everyone, welcome to this video. So in this video, we're gonna be basically talking about first we're gonna talk about big O notation, and then we're gonna check out how to do asymptotic analysis for big O notation. Yeah. So first, let us go and see what is a big O notation. So basically, whenever we have written any algorithm, so we have to find the efficiency of an algorithm. So how do we find an efficiency of an algorithm? So what is really mean by efficiency? So the efficiency, we do calculate the efficiency of an algorithm in terms of time complexity or else in terms of space complexity. So basically, these two tells an algorithm's resource usages. Okay, so we are not interested in calculating the concrete time taken by an algorithm, but basically we want to calculate the time complexity of an algorithm based in the terms of n, the n being the input which is given to the algorithm. So basically we'll be the time complexity we'll be calculating in terms of size of input, and similarly for space complexity as well we'll be expressing in terms of um, size of input. So this calculating time complexity and space complexity allows us to analyze the efficiency of multiple algorithms and choose the algorithm correctly for our computational problem. Okay, so this time complexity and space complexity expression in terms of input sizes gives rise to this concept called big O notation. So what does big O notation really means? So as I've said, time complexity will be in the expression of input size of inputs, so, input sizes. Okay, so big O notation is represents the upper bound of the time complexities. So we when we have time complexity which is of f of n, so it will give the upper bound of the time complexity which can be taken by the algorithm which we have written. So I will talk about what does I mean by upper bound by giving by taking an example. Before that, we're gonna see this one. So basically, the general notation, the general form which in which we write the big O notation is like big O of g of n. So g of n being the upper bound time complexity expression. Okay, so in it will be written in terms of size of input. Yeah. Now let us see what does I really mean by upper bound time complexity. So first, we're gonna take the an example. So the example which I took here is the insertion sort algorithm. So here is the computer program which is written in Java language. So this is the insertion sort. In this insertion sort, the idea of insertion sort is this. Suppose we'll be given an array. So the insertion sort idea is to sort the array elements of an array part by part. Suppose we'll be starting from the second element of the array, and we'll be going all the way to the last element of the array. So when we are in the second element, we will be sorting the first element and second element, and then we'll go to third element. Then we'll be doing the sorting first one, two, three, and then four. We'll be doing the sorting for one, two, three, four, and so on. We'll be going to n minus one, such that we'll do the sorting for the entire array. So this is the idea of insertion sort, and this is the computer program. This is the implementation of this algorithm. So over here, as we can see, we have two loops. One loop is to traverse from second element to the last element, and other one is to traverse back from j minus one to all the way to first element to do the sorting. So we the inner loop, the sorting logic, will only be implemented whenever if we take any consecutive pair of array, so if left side of the pair is greater than right side pair, we'll enter this. I'll just give an example. So over here we can see this is in this array. So we'll start from the second element, and over here first we'll be comparing these two consecutive pairs. So over here, if left side of the pair is greater than right side pair, we'll do the swapping. So only when left side is greater than right side, we'll do inside and we'll do the swapping. So similarly, we'll go on to this. So next, after we've done this, we'll be moving to next element, and then we'll be comparing these two elements. If left side is greater than right side, we'll do the swapping, and then we'll be, as it is 53 will be swapped here and 35 will be swapped here. Then we'll do the comparison of these things. If left side is greater than right side, we'll do the swapping. If not, we won't do the swapping. The loop will just end and we'll go to the next iteration in the of the outer loop. So this is the idea of this. We have basically have two loops. One loop will be entering anyway, the second loop will be only entering if left side value of a pair is greater than right side value. Okay, so we'll be doing the time complex. We'll analyze the time complexity of this problem. So to analyze the time complexity, we're gonna divide into two cases. One case is, suppose the input which has been given to the algorithm is already sorted in ascending order. So we have an array 1, 2, 3, 4, 5. We can see that it is already been assigned. It is already in ascending order. So in this case, even if we take any consecutive two elements which forms a pair, the left side won't be greater, the value of left side won't be greater than right side. So since due to that, we will never enter this inner loop. Okay, so we'll only enter this outer loop. We'll execute this line and this line. We'll be executing these two lines n minus 1 times. Okay, so we'll go from all the way from second element to n minus 1. So we'll be executing it for n minus 1 time, and we'll be coming out here. So in this case, the time complexity will be in the order of n. So basically, the time complexity grows linearly with the input size. So when input is already sorted in ascending order, this will be the time complexity. So now we have assumed a different case. The case is that if the list is already sorted, but it is if it is sorted in descending order, like 5, 4, 3, 2, 1. So in this case, if we take in any two consecutive elements, the left side is always greater than right side because it is already sorted in descending order. So due to this, so every time we'll be entering this loop. Sorry, every time we'll be entering the inner loop as well, and we'll be doing the swap. So due to this, when we are in the second element, we'll be doing swap of first two elements. So we'll be doing one swap, and when we go to this third element, we'll be doing two swaps, and we're doing fourth element, we'll be doing four swaps, and when we reach n minus 1, we'll be doing n minus 1 swaps. So basically we have, this is the number of times we'll be executing these instructions. So if you calculate all this, it will be like n of n plus 1 by 2 minus 1. So it will be like n square by 2 n by 2 minus 1. So we can see we got a quadratic equation. So the time complexity will be growing in the order of square of n. So basically it will grow, the growth rate is in terms of input size squares. Okay, so with the into here we have two different cases. With the change in input time, input complexity, that the how time complexity with the changes with the change in input size is different. So in case of when input complexity is of type ascending order, it will be like in linear. When it is all input complexity is of type descending, the time complexity is a quadratic equation. So it is growing in types of squares of input size. So if you plot this graph, if you plot the graph in this xy axis, the x being the size of input and y being the time complexity. So the only portion of the graph which we care about is the left side, right side portion, right side of this y equals to 0, because since size can't be negative, we only deal with the right side portion, this portion of this graph. So in this graph, we can see the this time complexity red line is for the array which is in descending order, and this orange line, this is the complexity for the ascending order array with the increase in input size. Yeah. So now we can say that this is the upper bound of time complexity and this is the lower bound of time complexity. Suppose if for size n, this is the lowest time it can take and this is the highest time it can take. So it can take any value between these two. So this is the upper bound and this is the lower bound. So for big O notation, as I said, big O notation represents the upper bound time complexity. So since we, in our case, the upper bound is this quadratic equation x square by 2, this thing. So we will be using this expression to calculate, to express our time complexity in big O notation. So and also, as we can see, this parabola dominates this line for majority of this positive x-axis. However, from y equals to x equals to 0 until almost like x equals to 2, this straight line is dominating the parabola curve. So, but anyway, this is like only the two instances, right? The when size is one and size is two. So the majority of the portion of in post axis, x-axis, the parabolic curve is dominating the straight line. So due to which we will be using this quadratic equation to represent our time complexity in big O notation. Yeah. So this is what I meant when I was saying upper bound time complexity. So time complexity of an same algorithm is changing with the change in input complexion. So now this might not be the case in for every algorithm. So there might, in some cases, what happens is it doesn't depend on the complexity of inputs. It only depends on the size of inputs, and sometimes it doesn't depend even on size of inputs. First, let us see two examples in which it won't depend on the complexity of the input. So, for one such example is the calculating the sum of an elements of an array. So over here, we are simply looping through the array, and we am calculating the number. Doing the sum of elements of this array, and then I'm returning the sum. So in here, whatever may be the complexion of this array, we'll be entering this loop and we'll be executing this instruction as number of times as the size of this array, and we'll be returning this. So in this case, the time complexity will be like in order of n. So the time complex. So this is the upper bound. This n is the upper bound, and also this n is the lower bound. There is no such thing like we have different upper bound expression, lower bound expression. We have only one expression. This. So similarly, this is another algorithm. Here the algorithm is about finding the pairs in a given array. So we have to find different combination of pairs. Pair means a two elements and a combination of any two elements from this given array. So for this, I have two loops. One is from I2 running from 0 to n minus 1, and other is running from I plus 1 to n minus 1. So for in this loop, for every combination of I and j, I am getting an array and I am creating a pair and I am adding to the list of array and returning the pair. So even in this case as well, whatever might be the complexion of this array, we'll be entering these two loops and adding our pair to the list. So in this case, we didn't have any condition on this for loop for running this for loop. While as in the case of insertion slot, For entering this inner loop, we have this condition for in this case, but we didn't have any condition, so we will be entering this loop anyway, whatever might be the complexion of input. So in this case, our time complexity will be in terms of quadratic equation. So basically, our time complexity will be in the order of square of input size. So this is the case. So the time complexity is nothing but an expression in terms of input sizes, and big of notation is nothing but the upper bound time complexity. So it is nothing but maximum time complexity for most of the input sizes. It is the time complexity which for which an algorithm can take for a given input size. The time complexity cannot be more than the value which is calculated by big of notation. So that is the idea of big of notation. It is nothing but the upper bound time complexity or the maximum time complexity which can be taken by a algorithm for a given input size. Since we have seen what is big O notation means, now we shall move on to the topic. What is how to do asymptotic analysis for expressing time complexity in big O notation? Yeah. So first we shall see what is asymptotic analysis really mean. So asymptotic analysis is nothing but the study of algorithms uh, behavior, I mean algorithms efficiency in terms of time complexity or space complexity as the input size is reaching infinity. So when input size is reaching infinity, doing the analysis of time complexity or space complexity of an algorithm is nothing but asymptotic analysis. Yeah, so this is what asymptotic analysis mean. So first we shall see some of the common names which we usually use in this concept. The first one is asymptotically positive functions. So this is term which we usually hear in this concept. So what is asymptotically positive function? Which function is called as this? So a function is said to be an asymptotically positive function. So such that the values of function should be greater than zero for every value after a certain point. In this case, let us assume this f of n function. So the values taken by this function should be greater than zero after a certain point called n naught. So the n naught should be a positive number. So after this positive number, if the values of this function is greater than zero, we can say that this function is asymptotically positive function. In other words, we can also say that the function should be positive for a very large n value. Yeah, here are some of the examples which we can see. First is the quadratic equation n square minus 2n plus 70. So this function is definitely positive. If we see the graph of this, it will be like after x equals to zero, after a certain point of x, this as n is reaching infinity, it will be positive forever. So similarly, we can see 2 n power 20 this solves well will be positive after n equals to 0 line. And the last example is n square minus n cube plus 2. In this case, as n is reaching after n equal to 0 line, so as n is reaching infinity, this will be negative. So we can say that this function is not asymptotically positive. So so in this case, for express for time complexity of algorithm, we will only consider asymptotically positive functions. Yeah, so this is what I mean by asymptotically positive functions. Yeah, now we'll see how to calculate the time complexity of an algorithm in big O notation by following these simple steps. So these are the four steps which you need to do. First step, we have to express the upper bound time complexity of an algorithm in terms of size. Let us say the size is n. Okay, so first we have to do this. In this case, since we if we take the example of insertion sort, we already have calculated the time complexity. So this is our upper bound time complexity, x square by 2 plus x by 2 minus 1. So we have already calculated our time complexity. So yeah, so now the next step is, so first after we done with calculating the upper bound time complexity, we have to identify the dominant term in this time complexity function which grows faster when n is reaching or infinity. Yeah, so we have to identify the term, and after that we have to drop the constant terms, and also we have to drop the lower order terms. Yeah, so this is what we have, this third and fourth step is like. So in here, this is our upper bound time complexity, the term which grows the fastest as x is reaching infinity. As x is infinity, the term which grows fastest is this x square. So this is the dominant term. So in third step, it is mentioned that we have to drop the lower order terms. In this case, this is x by 2, and also any constant. In this case, it is x minus 1. So we will be dropping these two, and our time complexity equation will now be x square in order of x square. Yeah, so here x being x or n, this is being the size of the input. So the resultant will be the time complexity in big O of notation. So we can say that big O of n square, this is the time complexity of this algorithm. The algorithm is this insertion sort algorithm. So this is the time complexity of this algorithm. Yeah, so this is how to express time complexity of an algorithm in big O of notation. So till now, I have been saying big O of notation is the upper bound, right? So here, this is the time complexity of insertion slot. So the big O notation time complexity doesn't say the time complexity of an algorithm at all. So it does say what's the upper bound of this. Suppose if you take n equals to 2, so it doesn't mean that n square it is like, if we say n square is like 4, right? It doesn't mean that the 4 is the time complexity of for n equals to 2. It doesn't mean that 4 is the upper bound of the time complexity. The maximum time it can take is the 4 units or 4 instructions should be evaluated. So that is the upper bound. It doesn't say for n equals to 2 this should be the time it should be taken, because the big O is all about the upper bound. So as we have already discussed, for if we take n equals to 4, so the lower bound will be the this line, which will be like 4 itself, and the upper bound will be like n equals to 4. So the time complexity will be anything between this. It can be for n equals to 4, it can be 4 to 16, it can be anything from 4 to 16. For n equals to 2, it will be like 2 to 4, it can be anything from 2 to 4. It doesn't mean, the big of notation doesn't tell the exact time complexity of an algorithm. It does only say the upper bound of the time complexity. Yeah, so keeping this in mind, usually this is the common way of expressing generically expressing the upper bound of a function. So in this case, the expression is as such, this f of n belonging to big O of g of n. So here what it means is, the f of n is the time complexity of an algorithm. So, and we are here saying that f of n belongs to the set or collection of elements of big O of g of n. Yeah, so here g of n is the upper bound time complexity. So the time complexity of the algorithm will be uh, always be less than the upper bound time complexity. So this is how we usually express it. And also we can also say that we can also, in other words, we can also say that here we can see f of n belonging to g of big O of g of n, it will hold true if this inequality holds true. So the inequality is like f of n should be less than equals to constant multiple of g of n. So time complexity of an this what is, in simpler terms, what does it tell is, the time complexity of an algorithm will always be less than, or at most the time complexity will be constant multiple of upper bound time complexity. So this is what it tells, this equation tells. So we can say that a function belongs to big O of g of n. If so, the time complexity f of n is less than equals to constant multiple of g of n being the upper time complexity. So this inequality should hold true for a value c which should be greater than 0, and this inequality should not be, it's not needed that inequality should be true for whatever the n value can be. So it can be true after a certain point, let us say n naught. So in simpler terms we can say that if we can say an function f of n belongs to big O of g of n, if so, this inequality holds true after a certain point, after a certain constant called n naught. After n greater than or equal to n naught, if this inequality holds true, then we can say that f of n belongs to big O of g of n. So let us first here take an example and understand it better way. So here we are saying 3n square plus 2n belongs to big O of g of n square. So this should be true only if uh, function f of n here is this quadratic equation less than equals to c of g of n. G of n is being the n square. Yeah, so if this equal inequality holds true after for a certain x or n for 10 n naught, we can say that this equation is correct. So in this case, this inequality holds true for c equal to 1 and n equal to greater. So here is the proof for it. So we can if we take for all n greater than equal to 1, we can say that this 3n square plus 2n plus 1 will always be less than 3n square plus 2n will make us 2n square, and 1 will take it as n square. So this will always be less than equals to 6n square. So this expression will always be less than equals to 6n square. So n square is nothing but the g of n. So we can say that this f of n is always less than equals to 6 into g of n. So for the 6 equal to 6, is equal to 6, and n greater than equal to 1, n greater than equal to 1, we can say that this inequality holds true. So we can say that this function, the upper bound of this expression is a constant multiple of n square. Yeah, so this is what it is about, this representation is about. And also one of the common convention ways, like since here we are saying f of n belonging to big O of g of n, the common way of representing is not this. The common ways of representing is f of n equals to big O of g of n. So instead of we are saying this equation belonging to this big O n square, we can also, we'll commonly convey it as this equation is being equal to this big O n square. So the here the case is that this equality which we are using here is not asymmetric. So it is asymmetric. It is meaning that if we say this is equals to this, but this doesn't mean that this big O of n square is equals to 3n plus 2n plus 1. So let us understand with an analogy. If we say Kiran is a human, it doesn't mean that a human is Kiran. So this human is a collection of species, right? So the same way here, this is one of the value of this, but doesn't mean that all the values of this is this. So this is here the equality is asymmetric. This is the, but this is just a common convention way which is being used in this concept in many books. Even if you see, this is the common way which we which how they will represent a upper bound of a function. Yeah, so in this video we have seen what is an big O notation means, and we have seen how to do what is asymptotic analysis, and then we saw how to calculate the time complexity in big O notation, and then we saw a common way of representing the asymptotic upper bound function for an function called f of n, and we have also took an example to understand this common way representation. Yeah, so this is for this video. Let us meet in the next video.